Je mentionne avant de commencer que mon exposé sera en anglais, mais mes transparents sont en français. So in order to maximize the mutual understanding of French speakers and non-French speakers, I was saying, welcome folks in the back, that the talk will be in English, but the slides will be in French, but hopefully everyone will understand something, and maybe someone will understand everything. So the talk is titled Being Reliable, but what's uncertainty. A different title might have been Reliability and Metacognition. So I'm interested in, so this is a sort of issue I've been interested in for years. I'm realizing now that it's sort of getting momentum in relation to other discussions that have been here and elsewhere, so it's a very nice opportunity to present this. So I've been interested in the way in which different norms for our belief may interact and maybe contradict each other. So one of them is, avoid error, and another one is, reach for truth. And a problem is that these two norms may seem to be only one norm, but possibly one of those maxims may just contradict the other. So there may be cases in which, if you seek the avoidance of falsity, you may fall short of getting truth, or many truths, maybe. And this, I think, has to do with the fact that it's part and parcel of the process of forming beliefs that we have to admit a sudden number of errors. I mean, this probably is just a fact about our knowledge, about the way we are constituted, that just forming beliefs in order to reach knowledge will involve the admission of errors. And maybe I'm giving what could be the punchline, but that, if you seek the avoidance of error too much, you might risk missing getting the truth right. So that actually will not surprise to use the very apt terminology that Julien Duton was using yesterday. This definitely falls in the ballpark of a consequentialist notion of knowledge, but I want to question the two norms that I've been mentioning, and there will be others along the way. So one norm which may seem to sort of, strike the right balance between the previous two is to say, we should aim for reliable beliefs, or having reliable belief-forming methods. And as a first approximation, I think having reliable beliefs could mean, having beliefs resting on a method which produces a high ratio of true beliefs. So, most, or maybe a sufficient proportion of our beliefs would be true, and that may count as, defining the notion of reliability. And I think that's, as a first approximation, this is the right notion of reliability. So a meteorologist, for instance, is reliable if he or she makes predictions that are, correct most of the time. Maybe a large proportion of the time. Reliability for a mathematician, of course, gets to be evaluated along many dimensions. Maybe because I'm better at making conjectures than proofs, I would say that if you make true conjectures most of the time, you count as, being a reliable mathematician to some extent. Now, I'm questioning now the notion of reliability in relation to metacognition, because you may think being reliable requires more than just having true beliefs most of the time. Just because you may have, true beliefs most of the time in ways that are, themselves lucky, that's questionable, but you could be relying on someone, who's sort of genuinely knowledgeable. You're not knowledgeable, but you sort of import lazily the knowledge you have. So in order to be reliable, you need some appraisal or assessment of the methods by which you're producing your beliefs. And that's already introducing a sort of dimension of metacognitive assessment. And I think also that you need, to the extent that some of your beliefs would be false and others would be true, you need an assessment of your own uncertainty. And I think, and that will be what I want to focus on, an assessment of the best ways to exploit the uncertainty you have. So yesterday in Jacques-Henri Vollet's excellent presentation, I got confused about what to call certainty or uncertainty, and Jacques-Henri explained to me quite rightly we need to distinguish various kinds of certainty or uncertainty. I think I'm going to, for most of the talk, I'm going to talk about the psychological notion of uncertainty, which sort of might have biased my own reaction to your talk yesterday. But let's put it this way: it may not be so essential for what I'm going to say today that if we think of yet further norms for our beliefs or even for our actions. If you think one of the norms, or the norm for our actions is knowledge, and if you think knowledge entails some form of certainty, and you grant me that it could be psychological certainty, it could be something stronger, like Jacques-Henri was saying yesterday, but then it would follow that certainty, even in that psychological sense, could be a norm of our actions. Of course, that need not be the case for many of the supporters of the knowledge norm, that psychological certainty is implied by knowledge, and therefore that need not be part and parcel of this. But for the examples that I'm going to discuss, it's, I think, non-problematic to equate cases in which there is certainty with psychological certainty with cases in which there is knowledge, in cases in which there would be failure of psychological certainty, to be cases for which there would be failure of knowledge in the strong sense, in the proper sense of knowledge. Okay, this is just a caveat. I hope it'll get clear. So what I want to do in this talk is basically focus on cases of uncertainty where error is unavoidable, since this workshop is about fallibilism and also, about certainty and infallibilism, but there are also there are negations. And I'd like to show that the norm of certainty, or you may, as I said, strengthen it to the norm of knowledge, would be suboptimal in some of those cases, right, where we are to make errors. So then I think a more useful norm is just have a capacity to assess the degree to which you're uncertain about what information you have. And I'll say more in the conclusion about this. But maybe there is material in this slideshow for more than one talk. So the first thing I'd like to do, so my core example and most of the discussion will be focused on cases that have to do with signal detection. So signal detection is a useful paradigm in psychology, but also in statistical decision making in the broad sense. And then I may say something about the notion of probabilistic adequacy or maybe accuracy in the second part, if I have the time. So the first thing I wanted to talk about is about the notion of a necessary lack of certainty, and maybe necessary admissions of errors. So as I said, if you think that avoiding error and reaching for truth are the same thing, one way in fact to disentangle the two maxims or norms is to look at situations in which a subject cannot really avoid making errors, or knows that she will not be able to do that. And Furthermore, cases in which it would actually be irrational or suboptimal to only make decisions on the basis of full certainty or on just knowledge. And I think obviously signal detection theory offers cases of that kind. And some of those cases I thought about a few years ago, more than 5 years ago, in work that I was doing on vagueness at the time, and that I've picked up more recently. So here is an example of a situation of signal detection, which comes from Don McNichol. You have a card game in front of you, or a deck of cards, I should say, in front of you. There are 4 and 50 cards, and the cards are really sort of we're not playing like it's not a regular deck of cards. It's just one where the experimenter painted or put some dots on the cards with a brush, and each of the cards had 1 up to 5 different dots. Okay. And you're given the distribution of those cards in the deck as a function of the number of dots that they had initially, right? So you know that 50 cards had only 1 dot initially, and 100 had 2 dots, and 150 had 3 dots, and 100 had 4 dots, and 50 had 5 dots. Okay, is that clear enough to everyone? Okay. And before the experimenter asks you to take the task, the experimenter decides to add a dot with a brush on half of the cards. And this will be done uniformly through half of the cards. So it means that, you know, of the 50 cards that had 1 dot, 25 will receive an extra dot. And of the 100 cards that had 2 dots, 50 are getting an extra dot, and so on and so forth, right? So we have 150 cards with 3 dots, half of them get an extra dot, and so on and so forth, okay? Now the task is the subject, so you learn what the experimenter did, you know the distribution, but then you will be presented with each of these 4 and 50 cards in a sequence. Now that you know the cards were shuffled, you don't know in which order they would come, but you have to report when you think a dot was added to a card, okay? And you have not to report when you think no dot was added to the cards, okay? So if you see a card, you see 4 dots, right? You may decide, well, it has 4 dots. It could be one of those cards which initially had 4 dots, or it could be one of those cards which initially had 3 dots, but one of those dots was added, right? So I have to make a decision. Should I, raise my arm and say, signal, a dot was added, or should I keep silent and say, maybe you didn't do anything to that card. So here is a clumsy but accurate representation of the histogram of those 2 distributions of noise and signal. So the blue distribution is actually the distribution of those cards that have not received any extra dot, okay? So you see that, 25 cards have 1 dot after the experimenter has acted upon the cards. You also see that 25 cards have now 6 dots, right? Because we know that half of the cards that had 5 dots received an extra dot. And you see that, there are certain proportions of cards that have 3 dots, which, might initially have not received any extra dot, or, have received an extra dot. And basically, the histogram in black represents the proportion of cards in each category that received an extra dot, okay? And that's, what is really sort of nice and lovely about those examples is that they are completely faithful to the, the sort of more involved cases of signal detection that are of casual use by psychologists. Now, let's assume also that, the experimenter leaves you the option of, reporting more than, signal or not reporting signal for noise. You may also use a third option as a response, like, I'm not certain, I don't know. And that third option we'll call the uncertainty answer, right? So now if you think that you now have 3 options for an answer, when you look at the histogram, it's very clear that when the 2 distributions do not overlap, so when you look at the tails of those 2 distributions, these are situations in which you have the psychological certainty I was mentioning, but also, by my assumption, you have knowledge of what's going on. So if you see only 1 dot, you know that the card did not receive any extra dots, so you're completely sure, you're completely certain that you can respond. You can avoid using the uncertainty response. You can avoid using the signal response. You basically know that it's a case of noise. You know what's going on. And likewise, if you see 6 dots on the card, right? Because in this case, you're sure that a dot was added to the card, right? Because initially there were only 1 to 5 up to 5 dots, and this one must have received an extra dot. But if you're in the middle area here, when the card has 2 to 5 dots, you're in this area, in this gray area where you don't know. So possibly you could decide the following. I'm going to use the sort of noise answer when I see 1 dot. I'm going to use the signal answer when I see 6 dots, and I'm going to use the uncertainty answer when I see 2 to 5 dots. And I think this would be completely faithful to the idea that you should only act upon the basis of what you truly know in this case. Okay, and if you do that, sorry, let me maybe try to go. Sorry, I'm getting confused. Okay, let me say this. If you do this, I think it's probably the previous slide. Yeah, if you do this. You can only hope to correctly classify the cards. Namely, you can only hope to classify 50 of the 450 cards because let's suppose, of course, that the uncertainty response in this case is sort of neutral. In terms of payoffs, I'm going to also use this notion of payoffs because it's part and parcel of the theory, and it was nice to see that it also appears in Julien Duton's paper yesterday. Let's say the contribution you make to the, let's put it this way, if you get as many points as you correctly identify cards, you get only 50 cards that you correctly identify as noise or signal. The other ones you're uncertain about, right? And so only 1 over 9 of all the cards are things you have a definite opinion about, right? The way in which signal detection theory works is usually to tell you don't have a 3-option response menu. You have only 2 options, report signal or report noise. And if you have only those 2 options, you can, of course, act as a sort of true belief maximizer, okay? And if you act as a true belief maximizer, you should consider the way in which you can optimize your decision to report something as a signal or as noise as a function of here. So you see here, x is the number of dots on the cards, and you see the probability of seeing x, right, if you're in a noise situation, or seeing x if you're in a signal situation, right? And if the card has only 1 dot, right, you see that you've got so many, this proportion as the prior proportion of that evidence given noise or given signal. And you can therefore, look at the sort of so-called likelihood ratio. Which is that in this case, it's just the probability of seeing what you see given that it's signal over the probability of seeing what you see given that it's noise. So we can abstract over the details. I think it's easier to understand if I go back to my histogram. So if I see 2 dots, right, on this example, you see that a third of the card that have 2 dots are signal cards, right? And 2/3 of those cards, right? So sort of 2 cells of that bar are actually noise in this case, right? So in this case, it would be sort of better. You have better chance of getting the truth if you report noise than if you report signal, okay? And you see that the same holds in this case, right? In this case, so the signal to noise ratio increases. So if you got now, 2 versus 3 are the odds of, getting signal as opposed to noise, or, 2/5 signal, 3/5 noise. But things sort of revert on that side of the red bar, right? And therefore, it's very rational. And it's actually, in fact, optimal as a strategy to decide the following course of action. If I see 4 dots or more, I'm going to report signal. If I see 3 dots or fewer, I'm going to report noise. Okay, so that is actually the optimal strategy in the following sense that if you look at, it's exactly the same kind of table that Julien was using yesterday. If you look at now the probability of reporting signal when it's actually signal, you get a 2/3 probability of doing that. And if you look, so this is the sort of probability of hits. And if you look at the probability of reporting signal when it's actually noise, it's only 1/3, right? So the probability of correct rejection is exactly the opposite. You correctly report noise when it's noise 2/3 of the time, and you only incorrectly report signal when it's noise 1/3 of the time, right? So in this case, you can correctly classify 2/3 of the cards, and you see that 2/3 is better than 1/9, and therefore this is a case where arguably relying on just categorical certainty is suboptimal versus making a more risky decision of acting on the basis of what you only believe is likely, as opposed to what you're sure is the case. Something Julien mentioned also in his talk yesterday is that the position of this so-called decision criterion is a function of the cost of false response and of the benefit of true responses. And exactly as Julien was assuming in his own paper yesterday, it's sort of standard to assume that costs and benefits are, equivalent for that kind of game. But you could also decide to, make the punishment or the cost for a false alarm actually greater than the benefit for hit, right? And if you do that, you're encouraging. We can skip over the mathematics, but if the cost is twice as much as what the benefit is for a hit, when it's a false alarm, it's actually rational to be stricter on your decision criterion, okay? And therefore, you would decide, to only report signal when, in this case, it's 5 cards or more, and it's noise otherwise, okay? So in that case, you're not as likely to categorize the cards in the right way, but at least you will optimize your benefits. And as you see, if I increase the cost of a false alarm even more, then I could be leading the subject to just rely on the certainty response. Okay. So since we started late, I think I have more time than what you told me. We started at 11:10, and I've been speaking for 23 minutes, so I think I still have 17 minutes before discussion. Thank you, Benoit. Okay. So strictly speaking, what I wanted to say is that uncertainty, as you could see from this example, arises when the two curves of signal and noise overlap. And you see that the degree of uncertainty is itself an increasing function of this overlap. And what I said is, as a rational subject in the case of this game, who would want to maximize the number of cards that they correctly categorize, would have an interest not to use the response I'm uncertain in cases in which this response is actually doesn't give the subject any payoff. So of course, one assumption, if I really put up the matrix of utility that I've been assuming, when I have three responses, I said, if you opt out and you say I'm uncertain, I'm assuming you get no point. If you correctly classify or if you correctly reject, then you get a point, right? So that's the situation where it's suboptimal to use the uncertainty response. But of course, things change if, let's say, I'm assuming a different payoff matrix where now the uncertainty response gives me 1 point when I correctly report the uncertainty, when I report uncertainty in the case of signal or noise, I get an incentive, let's say, to respond signal, but now there's this penalty for false alarms, and there is also this penalty for misses, right? If I fail to report signal when it's actually signal, then you can see that the cost of emissions and the cost of false alarms is more than just the benefit of correct responses or correct rejections. And here it seems to be a very rational strategy, and I think it's the optimal strategy to actually do what I was saying initially. So you will first, if you're sure that there's signal, report signal, because you get 2 points when you have 1 cards. If you're sure to get, noise, report noise, and again you get 2 points. And if you're in between, just report uncertainty, because at least you incur no cost, right? So you can only increase your benefits. So some of the, let me go to the lessons of this example. A lesson is that a subject who accepts to make mistakes can be on average more reliable, in the sense that I was first describing, of outputting a ratio of true responses in this case that is higher than a subject. So it would outperform a subject who would try to be accurate in the sense of fully accurate on each of the individual responses he or she gives than the former. Just as a recreational remark, I was in Stuttgart recently, and there was this nice citation by Hegel, which I could read in German, but I'm going to translate into English, which says that this fear from error might be error itself. I don't know where it comes from, but I thought it was nice that the Stuttgarter put this fragment of a Hegelian sentence in the front of the station. I thought maybe Hegel was thinking of signal detection. If he was, I think he had a point. Now, reliability as the average correctness of responses is, as you can see from this example, a function of the assessment that the subject has of the objective uncertainty, in which case I'm assuming the subjective uncertainty is really sort of read off the objective uncertainty because the subject is fully informed and fully rational. So the previous example and the two examples that I have, the one in which you have payoffs for being uncertain versus the one in which you have no payoffs for being uncertain, suggests that a subject who would fail to appreciate the uncertainty degrees to the right extent might give suboptimal responses, right, in both of the scenarios. So if subject wants to avoid too much error in the first scenario, he would be suboptimal. And if a subject sort of, fails to appreciate her uncertainty. In the second case, she would also be suboptimal. So here comes a remark that actually inspired a question I had to Julien yesterday. I think it might be useful in those discussions to introduce the distinction between acceptance and belief. So consider the case of a forced choice task, the one in which you can only respond signal or noise. So you could argue that the decision to report a signal, a card on which you see 4 points, is once you've settled on your criterion, only a form of acceptance, as opposed to just having any belief in the proper sense. In other words, you see a card, it has 4 dots, and you don't know whether it initially had 3 dots or 4 dots. So literally, you know that you're not sure about what's going on. However, you made your decision. I'm going to report, let's say, signal because it's 4 dots. But of this particular card, I have no belief, right, that it's actually a signal card. I made my decision relative to the deck of cards, right? I did not make my decision relative to that particular card. So here, I think it's actually useful and probably relates to some of the considerations that Julien was making yesterday, that I would say that a rational subject doesn't believe in sensu diviso of that particular 4-dotted card that it had an extra dot. Maybe he believes it in sensu composito, right? In the sense that relative to the full deck of cards, I have this belief that it's more likely to have a when I see 4 dots, it's more likely there being a signal as opposed to noise. So there's a hint to me that the preface paradox you were mentioning, Julien, yesterday has also that same structure. So let's leave that for discussion. Now, I have 5 minutes. We seem to be negotiating with my chairman here. Maybe I have more than 5 minutes. Let me say something about calibration. This is, in a sense, it could be a different talk, right? Because maybe some of you are disappointed by what I've said so far, right? You could say, well, we thought this is just a plea for, epistemic consequentialism, what I've been describing so far. But actually, I want to say something more. So Julien very nicely yesterday said, you may be a non-consequentialist for knowledge as a matter of general taste, but think that, consequentialism applies in some area. And I said this talk is about reliability and metacognition. And I think it's important that, maybe the norms, the sort of metacognitive norms, could be something of a non-consequentialist, flavor, as opposed to the norms that govern how we should make actions or assert things in a variety of contexts. So what I want to say now is I want to tell you something about the sort of broader project that I have, which concerns the assessment, therefore, we can make of our own uncertainty. And again, I'm thinking of cases where we know in advance that we are bound to make errors. And I think this is typically the case that meteorologists face when they need to make predictions about the future. They have no sort of capacity to see the future properly. They only have capacity to make predictions. And in this area, there is this paper, which of course some of you will know, by Glenn Breer, who has been so influential, about the definition of a score for reliability of judgments of confidence relative to the occurrence or non-occurrence of particular events. This is a paper that is a 3-page long paper in the Monthly Weather Review in 1950. It's very interesting because basically we have the same, I think, it is in the vicinity of signal detection, in the sense that an ideal subject, meteorologist, would be a subject who makes no error and who's 100% confident all the time, right, about each of the errors, about each of the responses or predictions he or she makes. But if the subject is not, that ideal subject, the subject knows that they can make errors, but they can have a more or less correct assessment of their responses. And there's this notion of Brier score, which measures the notion of relative reliability as a function of the distance between the degree of confidence in your response and the occurrence of the event we're talking about. So the example that Brier is actually giving in his paper is you make a series of 10 predictions about rain, whether there will be rain on particular occasions. And for instance, on that particular occasion, you are fairly confident, 0.7 confidence that there would be rain, but there's actually no rain. Here you're fairly confident there is rain, and so on. And what the Brier score does is compute the weighted average of, the squared deviation between the confidence level you have and the just indication level for the occurrence of the event. It's 1 when it's occurring, it's 0 when it's not occurring, right? It's actually an idea that goes back to Ramsey in a paper from 1926. Given a habit of a certain form, we can praise or blame it accordingly as the degree of belief it produces is near or far from the actual proportion in which the habit leads to truth. We can then praise or blame opinions derivatively from our praise or blame of the habits that produce them. And this is actually Ramseyan idea has led to the idea of calibration of the belief. So a belief is well calibrated if, over a sample of predictions you make, if you consider only let's say the predictions to which you gave a 0.2 level of confidence, in fact, only 20% of the events that over which you gave that degree of confidence are occurring events, right? So, and this suggests a correspondence between the frequency of occurrences of events and the degree of confidence you have. So subject, in this case, these are examples from actual predictions from meteorologists that have been examined by psychologists. These meteorologists over, several years of each number here is a day. So if you add up the days, it's more than, 4 years, and they are very well calibrated, as you can see. But calibration, I think, is a measure of the correspondence, which may not necessarily be a good or exclusive indication of the notion of reliability. And I thought of an example which I discovered then was already, I think, proposed by Goldman and Teddy Zeidenfeld. It's been discussed in a recent paper by Dunn. Not this particular example, but here is the example that Glenn Brier has in the paper. So Brier contrasts two subjects. One is the original subject with the predictions called Pred 1, and the other guy would be someone who really predicts there will be rain, but with low confidence every time. So I predict there will be rain. I have a 0.3 confidence level, and it turns out that only 3 out of 10 times is there rain in this case. So what you can see is that subject number 2 is very well calibrated in this case. You could think that the subject is making very good use of her own uncertainty in this case. But in fact, in terms of Brier score, the first subject is more reliable, because the more reliable you are, the closer you should be to 0 in terms of Brier score. And actually here, there's this big discrepancy. So if you look now at the plot of observed values as a function of the predictions they make, there is a striking discrepancy between the two subjects. So this very well calibrated subject is some of these 7 out of 10 times, right, missing on rain, and 3 out of 10 times giving rain. And the other guy, who's much less well calibrated, is able to actually make predictions assigned to each confidence level a particular prediction, right, which actually never occurs non-uniformly, right? So if I give 0.2 to my prediction, all the predictions I give 0.2 will, be rain events or no rain events. And this has been called resolution in the sort of posterior literature on the analysis of Brier scores. And it's actually nice because this example shows that a subject who would be perfectly, I don't know what to call it in English, resolved, could actually outperform a subject who would be perfectly calibrated. And obviously, you could maybe cook up an example where a subject could be perfectly resolved and be outperformed by a perfectly calibrated subject. But my point is that I don't think calibration can be the only assessment of the notion of metacognitive assessment for confidence. I will skip this because I know I've been abusing of my time, but I would just make two short concluding remarks. One is that this notion of reliability, I think, in the broader sense, not just the truth ratio of your beliefs, but the capacity to, have a correct assessment of your uncertainty, is not fully characterized in terms of calibration. It has to be characterized in terms of something else. Jeff Dunn, in the paper that I was mentioning, thinks otherwise. He thinks calibration is sort of capturing everything. And just to go to my overall conclusions, I think avoiding error and reaching for truth, as I said, can be intertwined goals, but they can sort of contradict each other qua norms, right? We saw that in a particular example. I think reliability defined in the first order sense as the truth ratio of my beliefs is indispensable but insufficient to characterize what's a reliable process. Examples from signal detection theory and the very short discussion I had of calibration suggest that something needs to guide the assessment we make of our uncertainty. And how to characterize exactly the metacognitive assessment of one's first-order reliability, I think, is a task that is facing all of us in this room and more and beyond. So I hope we can have a nice discussion about it. Thank you very much.